The concept of infinity has fascinated and unsettled humanity for as long as we can remember. The idea that time could continue forever, or that the universe might actually be infinitely large, is dizzying. Scientists have long struggled to gain a deeper understanding of infinity. And of all things, mathematics revealed a stunning insight that would turn everything upside down. There is something even greater than infinity. Because there is not just one infinity. There are actually several. And some of them far exceed our familiar idea of what infinity means. How can something that is already endless suddenly seem small? This super-infinity was discovered by the mathematician Georg Cantor around 150 years ago, forever changing our understanding of infinity. But don't worry, there is no need to be afraid of the math. We only need a few simple ideas involving basic numbers. The simplest form of infinity, and the one we are all familiar with, is the infinity of the natural numbers. Natural numbers are the numbers we all use for counting in everyday life. So 1, 2, 3, 4, 5, and so on. Everyone knows that in principle we can continue counting these numbers forever. There is no end. There are infinitely many of them. Things become strange when we look only at the even numbers among the natural numbers. There are clearly infinitely many of those as well. On the other hand, only every second natural number is even. This raises a question. Are there only half as many even numbers as natural numbers, even though both sets contain infinitely many numbers? The answer is just as simple as it is paradoxical. In intuitive terms, two sets are the same size if we can create a unique one-to-one correspondence between their elements. Take, for example, the set containing the numbers 1, 2, and 3, and the set containing the letters A, B, and C. We can create a unique correspondence between the two sets. The two sets are therefore the same size. If two sets are different sizes, such as the set 1, 2, 3, and the set A, B, C, D, then no such one-to-one correspondence exists. No matter what system we try, there will always be one letter that cannot be paired with a number. Interestingly, however, exactly this kind of one-to-one correspondence can be found between the even numbers and the natural numbers. To see this, we simply write down the first few natural numbers in a column. Then we multiply every number on the list by 2 and write the result next to it. On the right, we now have a list of all the even numbers. And this shows us that for every natural number, there is exactly one corresponding even number. Just as before, we have found a unique one-to-one correspondence between the two sets. This leads us to the astonishing conclusion that even though only every second natural number is even, there are exactly as many even numbers as there are natural numbers. This example shows us that these two infinite sets, although one appears to be twice as large as the other, are actually the same size. From this, Galileo Galilei concluded as early as 400 years ago that infinite sets could not be compared by size. He concluded that it simply made no sense to say that one infinite set was larger than, equal to, or smaller than another infinite set. Intuitively, this seems reasonable. But around 150 years ago, the great mathematician Georg Cantor disproved Galileo's conclusion. Cantor examined the set of real numbers, in other words, the entire continuous number line. The continuous number line clearly also contains infinitely many numbers. It includes all the numbers we can imagine and write down, such as 1, 2, 3, or even 7.51923. What makes it special is that we can examine an arbitrarily small interval, such as the interval from 0 to 1, from 0 to 0.1, or an even smaller one. Even within these tiny intervals, we find infinitely many numbers. No matter how far we zoom into the number line, we can always choose an even smaller interval, and that interval will still contain infinitely many numbers. By contrast, if we choose a bounded interval among the natural numbers, it will always contain only finitely many elements. It is completely impossible to keep zooming further into the natural numbers while continuing to find more and more numbers. So perhaps there really are more real numbers than natural numbers, even though both sets contain infinitely many elements. If there were equally many of them, as with the natural and even numbers, we should be able to find a one-to-one correspondence between the two sets. But as Cantor demonstrated with remarkable simplicity, no such correspondence can exist between the continuous number line and the natural numbers. Let us assume for a moment that such a correspondence did exist. We could then pair every natural number with exactly one real number and write them next to each other in an infinite list. But as we are about to see, there will always be real numbers that do not appear anywhere on this list. It is therefore impossible to assign a natural number to every real number. We can show this simply by constructing a new number that differs from every number on the list. For the digit before the decimal point, we choose 0. Now we take the first number on the list, and for the first decimal place of our new number, we choose 5 instead of 4. Our new number is now different from the first number on the list. We do the same thing with the second number. We look at its second decimal place, which is 6, and choose 7 instead of 6 for our new number. The new number is therefore also different from the second number. We continue in exactly the same way for every number on our infinitely long list. This gives us a new number that clearly differs from every number on the list. This number cannot appear on our list, even though the list is infinitely long. And this means that no one-to-one correspondence can be established between the natural numbers and the real numbers. No matter which correspondence we choose, there will always be real numbers that do not appear on the list, and therefore cannot be paired with any natural number. Even though the set of natural numbers is already infinite, there's another infinity that is even larger, the infinity of the real numbers. There must therefore be infinities of different sizes. The most astonishing part is that all the numbers we wrote on this list lie between 0 and 1. This leads us to the absolutely remarkable conclusion that there must already be more real numbers between 0 and 1 than there are numbers on the entire infinite list of natural numbers. The infinity of the natural numbers is known as countable infinity. The real numbers, on the other hand, could not be counted even if we had an infinite amount of time. This is why their infinity is called uncountable infinity. Mathematicians eventually proved that there are even more infinities, and even larger ones than these two. Today we know that there are infinitely many different sizes of infinity, and in fact, there are at least countably infinitely many of them. The idea that the universe might truly be infinitely large and contain infinitely many stars is already overwhelming. But would this be only a countable infinity? A simple number line between 0 and 1 already contains more numbers than there would be stars in an infinite universe, revealing an even deeper and more mysterious dimension of infinity. And yet Cantor's discovery teaches us that even infinity has structure, and that mathematics allows us to uncover its hidden architecture.